Hey guys, welcome back. Today we're not really going to do anything new. We're just going to add a little bit to yesterday's lesson. Maybe you can take the time to watch these videos that I worked out on the trickier ones, the more time-consuming ones. We're going to do more of the same today. For starters, I made a video on number 19 that I want you guys to watch, and I'm going to summarize a little bit of it right now. So number 19, I'm not going to work it all out here because I already made a video of it, but I want to remind you of a couple of things with sign charts. When you know you're doing a sign chart, if you have a square root in the problem or a natural log in the problem, then neon flashing lights should be going off in your head. As soon as you see a square root or a natural log, you got to remember you cannot take the square root of a negative number and you can't take the natural log of a negative number. So you should immediately go to your sign chart, whatever sign chart you're doing, whether it's first derivative or second derivative, and chop off a part of that graph. So for this one, number 19, if x were negative 3, we'd get 0, which is okay. But if it's anything less than negative 3, if it were negative 4, for example, then you'd be doing the square root of a negative number. So go to negative 3 on your sign chart and go right away, oh, anything to the left of that simply does not exist on this graph. There is nothing there. So regardless of whatever else you find in the problem, the graph does not exist to the left of negative 3 because you cannot take the square root of a negative number. Okay? So that's why number 19 had some, you maybe didn't understand the answer to it. But it also was a time-consuming problem to work out. So if you need help with actually working it out the rest of the way, then watch the video that I made on that one. Also, number 31 has a natural log in it. And it doesn't matter where the natural log occurs. If it occurs in the original problem, if it occurs in the derivative, or anywhere along the way, okay? As soon as there's a natural log in the problem, go to your sign chart, whether it's the first or second derivative, doesn't matter. Go to whatever's going to make this equal 0, which in this case is 0, and you cannot take the natural log of a negative number, so you cross off everything to the left of 0. And that does not exist. That graph does not exist left of 0. And then if you want to understand what your sign charts mean, take the time to put these in your graphing calculator and look at those graphs so you can see what happens. Okay? All right, if you have other questions, let me know. Maybe on some of the trig problems. There was one in your worksheet 2 days ago that had 4 answers instead of 2 because of looping around the unit circle a little bit. Don't worry about that too much if you didn't understand the extra 2 answers. But if you need me to work out more problems, please keep telling me, all right? All right, I'm going to move on to today's lesson, which again is not really new. All right, this one is just about understanding the lingo. So you're going to sketch a possible graph based on these characteristics, and understand that you may not get the graph all in one shot. You might have to do a little piece of it and erase some and try again. All right, so, and I might not get it the first time either. All right, so first of all, this graph only goes from 0 to 5, which means nothing should happen over here. And it should stop at 5. That's kind of weird. Okay, it's going to stop at 5 somewhere. All right, so there's nothing going on over here. That's kind of weird. All right, f of 3 is 1. There's a point right there. Got it. Check. All right, to the left of that, from 0 to 3, my graph, my first derivative is positive and my second derivative is negative. But you want to put that into words. First derivative positive. What word does that mean? First derivative positive means increasing, so it's going uphill. Second derivative negative, that means concave down. Concave down. So we need to be increasing like this, but do it in a concave down manner. So it's going to go uphill, but concave down. And that's from 0 to 3. So from 0 to 3, maybe something like that. Normally it would keep going like and have a asymptote, but this one has a clear point at 0, and I don't know what that point is. So that's a possible graph. That's all I got. Okay, could have gone lower, could have gone higher, whatever. All right, now let's see what happens to the right of 3. From 3 to 5, it's still first derivative positive, so it's still going uphill. But now the second derivative is positive, so it's concave up. So it's uphill, but doing it in a concave up manner. Okay. And remember, it has to weirdly stop at 5. So I'm going to go and stop wherever I want. That's a possible graph. And it has clear endpoints because of the weird way it was noted right there. So you're going to have two problems in your homework, 65 and 66, where you're trying to graph based on these characteristics. So remember, your first derivative issues, those tell you increasing and decreasing. Second derivative tells you concave up and concave down. Okay? All right, let's see what else I got. All right, this is a very common AP question. It would be a multiple choice question. And just make sure you read carefully. I've made it really obvious in the way I phrased it. But even if they don't use the word both. Oops, sorry about that. Let me go back. Technical difficulties. All right, even if they didn't say the word both, the word and is enough. So where is the graph both concave up and decreasing? Okay, they don't have to say the word both in order for it to mean the same thing. Okay, so basically for this one, you're going to do two sign charts, a double sign chart, and line one up on top of the other, just like we did for speed. Okay, so we're going to find first derivative decreasing. So first derivative would be negative. We're looking for that. And concave up, we would want second derivative positive. And it's usually easier to do your sign chart for the second derivative first and narrow down this piece first and then figure out this piece. Okay, so here we go. First derivative. Easy. 3x squared minus 12x plus 12. I'm going to go ahead to my second derivative. 6x minus 12. And you can see this is why I say do the second derivative part first. It's a lot easier to deal with. So second derivative sign chart. Okay, set my second derivative equal to 0. We get x equals 2. Checking around that, to the left of 2, we'd get a negative. To the right of 2, we'd get a positive. Well, we're looking for concave up. So now I've already limited. I'm looking for only this part of my answers. Now let's get the first derivative sign chart on there. And even though there's going to be more of my first derivative sign chart, I really only care about what's happening to the right of 2, because I already know that I needed it to be concave up. Okay, set my first derivative equal to 0. I can divide everything by 3 right now. If you didn't notice that, that's okay. Factor, and I believe I made a problem that I cannot factor, which would not be my choice. No, I didn't. It is factorable. I'm stupid. This is x minus 2 times another x minus 2. So we get x equals 2 again, which does not normally happen. This is kind of a weird problem. Okay, all right. So what's happening to the left of that? We'd get negative times a negative, which is a positive. And to the right of that, we'd get a positive. I am very confused by this problem. I guess my answer would be nowhere. I got to double check and see that I did this right. Hold on a second. So I double checked all my math, and I guess I just wrote a bad problem that I'll have to change the wording on, but I'm going to go ahead and answer it anyway. We're looking for where, all my math is right, by the way. We're looking for where f of x is both concave up, which was this, and decreasing. Turns out never. Therefore, if it's never decreasing, when will it be both things? The answer would be never. So this problem actually has, the answer is never. Now the reason is the graph, this is a cubic, and it ends up going like this. It's increasing the whole time. And right here, this is the point. That's the inflection point, which is 2. And it's increasing and increasing. And it's concave down, concave up. So at 2, that is where that inflection point is. And it does not change. The first derivative does not change. It's increasing the whole time. So I'm going to rewrite the problem and just change this word to increasing. Okay. So I'll go ahead and change it right now. But for this question, the way it was, my answer would be never. It is never decreasing. So it is never both decreasing and concave up. Now, if I change the question, change the word to increasing and concave up, now we would say from 2 to infinity. All right, got to change that. Let's see what else I got for you. All right, this is a common type of, this may even be a multiple choice question on the AP exam, and I just picked out pieces of it, part B and part D. This is pretty common where they do all the work for you and they just want you to know how to interpret it. So maximums and minimums. Maximums and minimums, that's a first derivative issue. So I'm going to do a first derivative sign chart using the first derivative and make sure you label it, okay? So find when the numerator equals 0, find when the denominator equals 0. The numerator will equal 0 when 1 minus x to the 4th equals 0. So 1 equals x to the 4th. And that's kind of like an x squared. It's basically at 1 and negative 1. Okay. Find when the denominator will equal 0. When you solve that, subtract 3, get x to the 4th equals negative 3. And you cannot take the 4th root, just like you can't take the square root of a negative number. So that doesn't give me anything. So all I need to worry about is the 1 and negative 1. So I'm plugging into the first derivative. And this denominator is squared. So anything squared is always positive. Therefore, I don't even have to think about that. So the only thing that's going to affect the sign is this guy. Plugging in a number here, in between 1 and negative 1, I'll plug in 0, and I get a positive. Plugging in a number over here, plugging in a 2, I'd get 1 minus 2 to the 4th. That's going to be a negative. If I plug in a negative 2, I get the same thing. So my local max would be at 1. And if I look at the choices and I see that they want the coordinates, then I would also plug the 1 in. Okay? My minimum would be at negative 1. And again, if I find out that I need coordinates, I would plug that into the original function, this guy. Okay, so that's maximums and minimums. Now inflection points. Remember, to be an inflection point, the second derivative has to change signs. And they often try to fool you with that one. People will find just where the second derivative is 0 and not check that it changes signs, and they'll get the answer wrong. So setting the numerator equal to 0, well, we're going to have a 0 because of that. Setting the other one equal to 0, 5 minus x to the 4th. So 5 equals x to the 4th. So x will equal plus or minus the 4th root of 5. Lovely. And setting the denominator equal to 0, again, you'll get a negative number. So I have my second derivative sign chart. I have 0, a negative 4th root of 5, and a positive 4th root of 5. Okay? Possible inflection points could be all three of these, but I don't know unless the sign changes. So now I'm checking around that. Okay, now 4th roots. Come on now. Well, I only really know 2 4th roots. I know 1 to the 4th is 1. So the 4th root of 1 would be 1. And 2 to the 4th I can manage. That's 2 times 2 is 4 times another 4. That would be 16. So basically I know the 4th root of 16 and I know the 4th root of 1. Well, the 4th root of 1 would fit in here and the 4th root of 16 would fit in here. Okay? So plugging in to my second derivative. If I plug in the 4th root of 1, or 1 for that matter, then this is negative, this is positive, and this is positive. So that's going to be a negative. If I plug in the 4th root of 16, the 4th root of 16, keep in mind, the 4th root of 16 is 2, okay? If I plug in the 4th root of 16, or 2, this is negative. The 4th root of 16 raised to the 4th is going to bring me back to 16. So that's negative. and this is going to be positive. Negative times negative is a positive. Doing the same thing, checking with the negative numbers. Now I'm going to plug in negative fourth root of 1. So the fourth root of fourth root of 1 is 1, but now I want the negative version. So I'm plugging in a negative 1, basically. Plugging in a negative 1, this will be a negative times a negative, so that's a positive. Plugging in a negative 1 here, you get 1. So that's a positive, and this is also going to be a positive, so that's positive. And last, negative fourth root of 16, plugging in a negative 2. So plugging in a negative 2 up here. This would be a negative 8 times a negative, that's a positive. Plugging in a negative 2 here. It's also the fourth root of 16 to the fourth, so that's 16. And 5 minus 16, that'll be a negative. And here, this would be 3 plus the fourth root of 16 to the fourth is 16, but that's a minus in front of it. So that's going to be 3 minus 16. So that's a negative cubed, which is still a negative. So that's 2 negatives altogether, which makes a positive. So put it all together. Where are my inflection points? There are only 2 of them because the sign changes only here and here. So my inflection points would be at 0 and positive fourth root of 5. So that last problem that I gave you was just a possible like AP type question. You don't have anything like that in your homework. Your homework is pretty much just like what we did yesterday, more of the same, okay? And your homework has 2 problems where you have to try to figure out what the graph looks like. That's these 2. So let me know if you need me to work out any videos, and good luck, everybody.